Hello students, I welcome you on behalf of Sri Jayendra Rank Zone classes. In previous lecture, we have seen the reflection of light, the reflection by plane mirror and the spherical mirrors, the image formation by concave and convex mirrors, the mirror formula, etc. Now, let us see the phenomena of refraction. First of all, let us understand what is refraction. Whenever light rays enters from one medium to another medium, whenever light travels from one medium to another medium, its speed will change. So if light is incident obliquely on any surface separating two medium, the light will change its path. This phenomena is called refraction of light. Now, the factor which decide whether the speed will increase or decrease is refractive index. Refractive index is the property of material that give us the idea about optical density. So optical density of any medium is given by its refractive index. It is denoted by mu or n. If refractive index is more, then medium is denser and speed of light is lesser in that medium. The refractive index is defined as speed of light in vacuum to the speed of light in given medium. Here C is 3 into 10 power 8 meter per second. V is speed of light in given medium. Refractive index of any material is dimensionless. If we compare speed of light in given medium with speed of light in vacuum, then this refractive index is called absolute refractive index. Let's say we have two mediums, one with refractive index N1 and other with refractive index N2. If we want to compare the optical density of these two media, we can find their relative refractive index. Relative refractive index of medium 1 with respect to medium 2. It is denoted by N12 and it is the ratio of N1 and N2. We can write N1 as C upon V1 and N2 as C upon V2. So N1 by N2 will be equal to V2 by V1. V is F lambda. Medium to medium, frequency of light will not change. So V2 can be written as F lambda 2 and V1 can be written as F lambda 1. So this will give us the ratio lambda 2 by lambda 1. So N12 is N1 by N2 or V2 by V1 or lambda 2 by lambda 1. The refractive index of air is approximately 1. Absolute refractive index of any medium is always less than or equal to 1. Because speed of light is maximum in vacuum and in any other medium, its speed is less than c. So this ratio will always be greater than or equal to 1. There are some examples. The refractive index of glass is usually taken as 3/2, that is 1.5. Refractive index of water is 4/3, that is 1.33. Now let us understand the laws of refraction. Let's say this is a surface separating two medium. If light ray is incident at an angle I with normal from medium having refractive index N1, and it is transmitted in another medium having refractive index N2. So this ray is called incident ray, and the transmitted ray is called refracted ray. Angle made by incident ray with normal is called angle of incidence, and angle made by refracted ray with normal is called angle of refraction. The first law states that incident ray, refracted ray, and normal at the point of incidence lie on same plane. The second law is called Snell's law. Snell's law states that the ratio of sine of angle of incidence to the sine of angle of refraction is always constant for given pair of media. This constant is given by refractive index of medium 2 with respect to medium 1 and 2, 1. Cross multiplying this 2, we can find N1 sine I is equals to N2 sine R. N1 is the refractive index of medium from which light ray is incident, and N2 is refractive index of medium in which the light is refracted. Here, we know that as light travels from one medium to another medium, it will change its path, it will change its direction. So basically, it will bend. So we can also define bending of light as refraction. We can have two possibilities of light bending. Either light will bend towards the normal, as this case, or it can bend away from the normal, as in this case. It will depend on the refractive index of two mediums. In case 1, when light ray travels from one medium to another, it is moving towards the normal. So, light is traveling from rarer to denser. If light travels from rarer to denser medium, then it will bend towards the normal. And the reverse case is when light travels from denser to rarer, it will move away from the normal. In case 2, light is moving away from the normal. That means it is traveling from denser to rarer medium. So we can say that N1 is greater than N2 in this situation. Wherein first case, light is moving towards the normal, so it is traveling from rarer to denser medium. So we can say that N1 is less than N2 for case 1. Now, light is incident on the surface of rectangular glass slab of thickness T. Due to refraction, there will be some deviation in the path of light ray. Here from the figure we can see that incident ray is incident on glass slab at point A. Here I is angle of incidence. In this situation, light is traveling from air to glass. Glass is denser compared to air. So light is traveling from rarer to denser medium. So it will move towards the normal. This dotted line is the actual direction of incident ray, but light is moving towards the normal and it will travel on path AB. Now, this light ray AB will behave as the incident ray for the opposite surface of glass slab at point B. Now again it is moving from glass to air. Glass is denser and air is rarer, so it will move away from the normal. So finally, this light ray is finally refracted light ray. The dotted line shown with black color is the actual direction of incident ray, and let's say BP is the finally refracted ray. Here we will prove that these two paths are parallel. So light is simply laterally shifted due to glass slab. So let us first prove that these two light rays are parallel to each other. At point A, we can apply Snell's law. So let's say refractive index of air is 1 and refractive index of glass slab is n. So we can write sine I is equals to n sine r. This is equation 1. Now at point B, again we will apply Snell's law. These are vertically opposite angle. If this is angle of refraction r, then this angle will also be r. So we can write n sine r is equals to the angle made by finally refracted ray with normal is called angle of emergence E, and that ray is called emergent ray. So n sine r can be written as sine E. This is equation 2. From 1 and 2, we can write sine I is equals to sine E. So angle I is equals to angle E. Here these two rays makes same angle with same line or same normal. So we can say that these two lines are parallel to each other. So due to glass slab, light is reflected, or it is light is parallelly shifted. That parallel shift is called lateral displacement. So the lateral displacement is the perpendicular distance between these two parallel light rays or parallel paths. We have drawn one normal BC on the actual direction of incident ray. Now, in triangle BCA, we can see that this angle is I minus R. That is called angle of deviation R. In triangle AMB, we can write cos R is equal to adjacent side upon hypotenuse. Adjacent side is AM. So in triangle AMB, we can write cos R is equal to AM by AB. AM is the thickness of glass slab, that is T upon AB. So we can write that AB is equals to cos R divided by T. Now, in triangle ABC, we can write sine I minus R is equal to BC divided by AB. Here BC is the lateral shift. Let's say it is delta or it is D upon AB. So lateral shift D is equal to AB into sine of I minus R. AB can be written as cos R by T it will be T upon cos R. So T upon cos R into sine of I minus R. So this is the lateral shift. Now let us see the concept of apparent depth. We have observed that the surface of water appears less deeper than its actual depth. This happens due to the refraction of light. Now, let's say there is object O placed at the bottom of water at depth T. Now, lights are coming from this object. Will move from denser to rarer medium at water-air interface. As they are moving from denser to rarer, they will move away from the normal. Now, when the extended refracted rays will intersect each other, the image of this object is created. So image is created at point I. Object is at O, but image is created at point I. So there is shift of the object in upward direction. So we will feel that base of the container or depth of container is lesser. Let's say that is T dash. That is called apparent depth. Apparent depth is defined as real depth upon refractive index of water with respect to air, or say real depth upon refractive index of medium 2 with respect to medium 1, where medium 2 is the refractive index of denser medium and N1 is the refractive index of rarer medium. So we can write shift delta T is equal to real depth minus apparent depth, that is T minus T dash, that is 1 minus 1 upon N into T. Now, if we are observing from any denser medium, in previous case, the observer was in rarer medium and object was in denser medium. But if the case is different, then there will be apparent height. The actual height is lesser than the apparent height. Here, let's say fish is observing a bird in air. The actual height of bird is T and its apparent height, the height at which it appears to the fish, is T dash. So T dash is apparent height. Here, the apparent depth or apparent height will be equal to real height into N21. Again, here N2 is the refractive index of denser medium and N1 is the refractive index of rarer medium. And the apparent shift will be real height minus apparent height. Now, let us understand the concept of velocity of fish and bird. Let us assume in a lake, there is a fish at depth X and bird is in air at height y from the surface of water. In case 1, we want to find the velocity of bird with respect to fish. If bird is moving towards the surface of water with some speed, what will be its speed seen by the fish? First, we will write the position of bird with respect to fish. Let's say that is RBF. It is given by X plus this apparent height will be equal to N21 into Y. Differentiating both the side with time. Suppose dRBF by dt is equals to x is constant as fish is not moving, so x 0 divided by n to 1 dy by dt. So this is the velocity of bird with respect to fish is equals to n to 1 into actual velocity of bird. Now let us take case 2 in which we want to find the velocity of fish with respect to bird. Again, we will write the position of bird with respect to fish. Sorry, position of fish with respect to bird. So RFB is this much depth is y plus this depth will be equal to n12 into x. Again, differentiating both this side with respect to time, we will get velocity of fish with respect to bird. If bird is stationary, then dy by dt will be 0 n12 into dx by dt, that is actual velocity of fish. What happens if light is incident on the combination of multiple immiscible liquids? Let's say we have 3 different liquids of a refractive index N3, N2, N1. They are immiscible and they are filled in container. Depth of liquid 3 is D3. Depth of liquid 2 is D2 and depth of liquid 1 is D1. So the apparent depth here, total depth is D1 plus D2 plus D3. It is the real depth. The apparent depth will be D1 upon N1 plus D2 upon N2 plus D3 upon N3. And if we want to find the shift of image, that will be equal to D1 into 1 minus 1 upon N1 plus D2 into 1 minus 1 upon N2 plus D3 into 1 minus 1 upon N3. Now let us understand the phenomena of total internal reflection. Whenever light ray is traveling from denser medium to rarer medium, it will bend away from the normal. And whenever light is incident on any surface, some part of the light is reflected, some part is refracted. Now, if we gradually increase the angle of incidence, the light ray will keep moving away from the normal, as seen in the figure. In first case, we have incident light ray normally. In second case, we have increased angle of incidence. So this refracted ray is refracted at angle R. Now, if we keep increasing the angle of incidence, at certain angle of incidence, the refracted ray will make angle 90° with normal. That means angle of refraction will be 90°. This angle of incidence at which we are getting angle of refraction 90° is called critical angle. Here I equal to C is called critical angle. Now further, if we increase the angle of incidence, then light ray will get reflected back in the same medium. So here there is no light that is moving away or moving in another medium. Completely light is reflected in same medium. This phenomena is called total internal reflection. So let us define the term total internal reflection. When light is traveling from optically denser medium to optically rarer medium, and if it is incident at an angle I which is greater than C. C is critical angle. Light ray is completely reflected in same medium. This phenomena is called total internal reflection. And what is critical angle? It is the angle of incidence at which angle of refraction is 90°. This angle of incidence is called a critical angle. Now, if we want to find the critical angle, then we can apply Snell's law in third situation. So, N2 sine C is equals to N1 sine 90. So, sine C will be equal to N1 by N2. Critical angle is equal to sine inverse of N1 by N2. Here N1 is the refractive index of rarer medium and N2 is the refractive index of denser medium. So, what are the conditions for total internal reflection? That is also known as TIR. The first and most important is light should travel from optically denser medium to optically rarer medium, and angle of incidence should be greater than critical angle. C is critical angle. So this are the conditions for total internal reflection. Now let us see the applications of total internal reflection. The first application of TIR is mirage, the formation of mirage. Mirage is an optical illusion observed in desert on hot summer days, due to which a person see a pond of water some distance ahead of him, in which the surrounding objects appear inverted. It is due to the total internal reflection. This effect can also be seen on road in hot summers, that you will feel there is water on the road. This happens because during hot summer days, the air which is near the ground is warm, hot air, so it is rarer, and above that, the gradual layers are of cold airs. So, light ray travels from object, then it will pass through optically denser to optically rarer medium. So on each level, there will be constant bending of light. Just above the surface, there will be the total internal reflection of light. So the person will see image of the object on ground, which will create an illusion of having water or any water body like pond on the surface. The other application is prism. The prisms are designed to bend the light by 90 degree or 180 degree using total internal reflection. In first case, we have changed the direction of light by 90 degree, and in second case, this the direction of incident ray. They are incident normally on this surface, so there will be no refraction at that point. Then at the other surface, if they are incident at an angle more than critical angle, then lights will get totally internally reflected. So finally refracted light rays are exactly in opposite direction. This kind of phenomena or this kind of application is used to invert the images. The next application is brilliance of diamond. The brilliance of diamond is due to total internal reflection of light. The critical angle for diamond is very small, approximately 24.4 degree. So once light enters a diamond, undergoes total internal reflections inside. By cutting the diamond suitably, multiple total internal reflections can be made to occur, and we can make the diamond more shiny. The next application of The total internal reflection is optical fiber. Optical fiber works on this principle of total internal reflection. They are made from high quality composite glass or quartz. Optical fiber consists of a core, cladding, and a buffer. The refractive index of core should be inside is core and outside is cladding. So refractive index of core is higher than that of cladding because at this point light is traveling from core to cladding. We want total internal reflection at this point because if light will refract, then the information which is in form of light will move out of the fiber cable, and if light is absorbed, then there will be loss of information. So we do not want refraction or absorption, we just want complete reflection of light. So here TIR is used. To have the TIR, the refractive index of core must be greater than refractive index of cladding, and angle of incidence at each point should be greater than or equal to critical angle. Now, where optical fibers are used? Optical fibers are used in communication system, they are also used to see the internal parts of human body. Now, let us understand how transmission through optical fiber takes place. Let's say this is cladding and this is core. Refractive index of core is N1 and refractive index of cladding is N2. Now, light is incident at certain angle from air. Its angle of incidence is I. At this point, light is traveling from air to core, so it will refract. It will move towards the normal as it is moving from rarer to denser medium. This is angle of refraction R. On the surface separating core cladding, light is incident at an angle R dash. At this point, R dash should be at least equal to critical angle or more than that. Light is completely reflected, and in this way, the transmission takes place. Now, what should be the relation between incident ray N1 and N2? First, we will apply Snell's law at point A, where light is traveling from air to core. So, refractive index of air into sin I is equal to refractive index of core into angle of refraction is R. Now, let's say this point is B and this point is C. Angle A is R, angle B is R dash, and angle C is 90. So in triangle ABC, we can write R is equals to 90 minus R dash. So refractive index of air into sine I is equal to N1 sine of 90 minus R dash. Sine of 90 minus R dash is cos R. So that will be N1 cos R. So N sine I is equals to N1 cos R. Cos R can be written as under root 1 minus sine square R dash. So taking square on both the side, N1 square into 1 minus sine square R dash is equal to refractive index of air square into sine square I. Sine square R dash will be equal to N1 square minus refractive index of air square into sine square I divided by N1 square. So sine R dash taking square root on both the side, N1 square minus N R square sine square I divided by N1. Now for TIR, R dash should be greater than or equal to critical angle. And here critical angle is equal to sine inverse of N2 by N1. So putting this value, we can write sine R dash should be greater than or equal to N2 by N1. Putting the value of sine R dash and finding the angle of incidence, I should be less than or equal to sine inverse of under root N1 square minus N2 square divided by refractive index of air. So this is the condition for angle of incidence to have TIR at core cladding interface. Now let us see the case when a source of light is kept inside the medium. Let's say this is a water body. Source is kept inside the water at depth h. The lights will be traveling in this way. We can see a circular shape on the surface of water due to this source of light. This circular disc shape will be illuminated. Meaning of this is that light is not traveling from water to air in other parts of the water. It is coming out only from this circular part. So what is the reason? At this point, the light is incident at critical angle. At this end points, let's say AB, light is incident at critical angle. For further incident rays increased, that means light rays are incident at an angle greater than critical angle. So light will not transmitted in air. It will be completely reflected to water. We want to find the radius of this circular disc shape. So here this depth is given h. Light is incident at an angle of critical angle C. So this angle will also be C. This height is h. We want to find the radius r. We can write sin C as refractive index of air, that is 1, divided by refractive index of water, let's say that is n. Now, in this right angle triangle, we can apply trigonometric, that is tan C is equals to R upon H. So R is equals to H tan C. Tan C can be written as sin C upon cos C. Sin C upon cos C can be written as 1 upon under root 1 minus sin square C. But sin C is 1 upon n, so put the value under root 1 minus 1 upon n square. So R is equal to H 1 by n divided by n square minus 1 divided by n square. So R is H into 1 minus n 1 upon n under root n square minus 1 divided by n. So R can be written as H upon under root n square minus 1. This will be the radius of the illuminated disk. If you have been asked that a fish is inside a pond and it sees the outer world as circular horizon, what is the radius of that circular horizon? This will be the same formula for the circular horizon also. Radius of circular horizon as seen by fish. So this is all for today. Thank you.